we're done with the AI assignments. Those were only through Unit 5, only for the first half of the semester. So at this point, the goal is you have been shown all of the different ways that you can implement AI, not just shown, but forced to implement. So now you know whether it's actually helpful for you or not. And you know how to make it more helpful for you, hopefully, than you did before coming into this class. So there are no more guardrails, no more bumper lanes. If you want to use AI, you now have the tools to figure out the best way to use it. That being said, there is a midterm reflection on the AI assignments. So that midterm reflection, if you guys remember, you either opted into using your data or you opted out of using your data. Our course lead, Ryan Holcomb, is doing a research on implementing AI intervention in the classroom. Your midterm reflection is one of the most useful parts in his research. He'll use it to gather qualitative data about how useful it was. So be honest, because no one here is grading you on whether you actually got what we hypothesized you'd get out of it or not. Be honest so that we can get good data on it. If you haven't already, feel free to do that. You'll get points for it. It's still graded. Okay. And then, like I said, midterm is still kind of ongoing, so we'll come back and talk maybe Wednesday, maybe next week, Monday, about how the midterm went and how it can guide us from here on out. The final is cumulative. Yeah. Although you're going to notice that the stuff we go on to talk about through the rest of the semester, it kind of hinges on everything we talked about already. Chemical formulas, concentrations, structures in a way, but it is cumulative. So you will see those concepts come back. Other questions? We're moving into chemical reactions today. So I wanted to show you guys some chemical reactions that show up on my Instagram that I save. Just to show you guys that chemical reactions are very different from each other and all very cool. I'll probably let this one play through one more time. I'm curious what you guys already know about chemical reactions, or what you think about chemical reactions, what you think they are, or what questions you have on what chemical reactions are. By the way, this reaction is nitric acid and copper. You guys will actually get a chance to do that if you're in the lab class this semester. You'll do this exact process, and then you'll follow it with more reactions afterwards. This is producing that red gas, which is nitrogen dioxide, NO2. And you can see there's a lot of pressure that's building up, so it bubbles air out. And then as the reaction dies off and the pressure decreases, it sucks that water in. And you can see the copper ions, copper nitrate or copper hydroxide that are in there. Copper makes some really beautiful ions. Here's another chemical reaction. This one is more so just a modeling of what a chemical reaction is. And what you'll notice about this is actually an organic reaction, not necessarily one that you would be predicted to understand today. But I want you to notice something about the bonds in this chemical reaction. The atoms are changing in the chemicals. So this chemical starts with 2 carbon atoms and maybe like a halogen, and then it goes to 2 carbon atoms and an oxygen. But the atoms aren't really governing the chemical reaction at all. It's the electrons that are resulting in the chemical reaction. So you see that oxygen comes in with a lone pair, shares it with this carbon, and then it creates kind of these half bonds. And then this halogen takes the electrons from this bond and leaves as an anion. So the atoms don't really govern chemical reactions so much as electrons govern chemical reactions. This one was already running. Let's see if we can get it from the beginning. Sulfuric acid, ethanol, and potassium permanganate. I'm not sure you guys need to know potassium permanganate as an ionic complex. Violent, explosive even, right? Releases a lot of heat, produces flames. This is another technically organic reaction, but it's a redox reaction. And it releases so much energy that you can see it's igniting some of the ethanol that hasn't even reacted yet. And then this is another chemical reaction. I really like this one. This is a precipitation reaction. So he's put two salts on either side, and then in the middle, as those salts dissolve and they move through the water droplet, you see that a new salt is actually forming. This is a different combination of salts. That yellow salt in the middle is a new salt that wasn't there before. Okay, I think that was it, right? So just an example of chemical reactions. A lot of them have some pretty cool colors. But in a lecture class, it's usually just on paper, so you don't get to see all the cool things that the reactions are doing. By the way, one of these reactions, they said they pushed in ferrous sulfate, which is not nomenclature that you were taught or expected to know, but that's different from ferric sulfate. Do you think that you could guess, out of the two charges of iron that you know, do you think you could guess which of these is ferrous and which of them is ferric? What would you use?
I'd say, because you said 8 and ick go together, I and us. And since 8 is bigger than ick, I would say
So you said ick is bigger than us?
Yeah.
For instance, we had sulfite and sulfate, which made sulfurous and sulfuric. And so you're going on more oxygens, gets ick instead of us. But there's no oxygens involved, is there? So you're just going by the charge, 2 plus versus 3 plus. We're actually going to talk about this in this unit on reactions, oxidation states. We can say that this sulfur is more oxidized. It has a higher oxidation state, and that makes sense because there's oxygens in the compound, whereas this has fewer oxygens, a lower oxidation state. But there's no oxygens here, so we're going to learn how oxidation state talks to us about what charge an ion has. And you are right, that the oxidation state that is more positive is more oxidized, and so ferrous, ferric, sulfate. Okay. I have some handouts for you guys, double-sided. And I want to open the floor. What do you already know about chemical reactions? What do you not know about chemical reactions? And what do you not know that you don't know about chemical reactions? You guys know nothing about chemical reactions? Alina? All right, class, you can go. Alina, you hit it on the head. I mean, you covered everything. New chemicals are produced that were not there before. And that's as simple as changing one chemical bond, or even just changing where the electrons are. Taking a metal like magnesium and turning it into an ion like magnesium 2+, that is a chemical reaction. You're allowing electrons to change where they are. Conservation of mass says you can't have more weight in the product or in the starting material. It has to be balanced. So we're going to have to look at how our elements balance, how our mass balances. What else did you say? Energy is transferred. Sometimes energy has to go in to make those new chemicals. Sometimes energy goes out when those new chemicals are made. Very good. Can you guys give me an example of a chemical reaction that you know? Do you have breakfast today? That's okay, me either. But imagine you had breakfast today. Any chemical reactions in that? Are you alive right now? Any chemical reactions in that? Biology is truly just applied chemistry. So the act of being alive implies that you are doing chemistry. Give me another one. Can't be hard. Give me an example of a chemical reaction. I'm going to hold off on you a little bit. Feel free to lean into any of the examples I kind of hinted at. One example and we'll move on, but not from Alina. She taught my whole lecture already. Love it. The baking soda volcano, right? You take some baking soda, you pour your vinegar on it, you produce a bunch of gas comes out of it, and water. Baking soda volcano is an acid-base reaction. Awesome. Okay, now we'll move on. Thank you. So we are starting up Unit 6. We're at the beginning of Module 14. We're looking at chemical reactions. I do want to point out, I'll be abbreviating reactions throughout this with this abbreviation RXN. I got to be honest, when I first saw that abbreviation, nobody told me what it meant. So I was just sitting there confused for a long time. What is RXN? But when you try to pronounce it, reaction. At the top of this handout that I've given you guys, you'll see that there's a generic equation. And to be fair, this generic equation is just one that I wrote up. It's not anything special in particular. In fact, I could see how this generic reaction may even leave you with some questions. This generic reaction doesn't have any actual chemicals, right? C and B, I guess those are chemical symbols, carbon and boron. D is actually a chemical symbol for deuterium, which is an isotope of hydrogen. It has one neutron and one proton, but A is not a chemical. So these are just placeholders for chemicals. Sub in H2O for C. Sub in copper 2 sulfate for A. A chemical symbol gives you these species that undergo a reaction, which are called reactants, and these species that are produced by a reaction called products. We have these plus signs. And we say that these plus signs separate the species in the reactants or the species in the products. And I would encourage you to get comfortable with using that word species to describe chemicals. It's not like species in biology. There's no like family tree here. We just say one chemical, that's a chemical species. Then you have another chemical. And then we've got these, this reaction arrow. True or false, the reaction arrow always has to point from the left to the right. No, yeah, that's false. It's very common to see that, but it's not necessary. True or false, the reaction arrow always points from reactants to products. That is true. Yeah, it does point from reactants to products, but there are chemical reaction arrows that are pointed in both directions, not just in one direction or the other. So how then can we say that it always points from reactants to products? What that says is when these species react, they produce these products. And when these species react, they produce these products. Both sides are reactants and products, depending on which chemical reaction you're interested in investigating. We brought up baking soda and vinegar. Vinegar on its own kind of goes through chemical reactions, an equilibrium reaction. Some of that acetic acid will react with water to make hydronium and acetate. So we have acetic acid and water, and it makes a conjugate product, acetate and hydronium. But now if these two chemicals run into each other, they can react to form these products, which are the initial reactants. So it is true that this always points from reactants to products, but in some cases, many cases, both sides are both reactants and products of different chemical reactions. Okay? What else do you guys notice in this generic chemical equation? Yeah, we've got phases in there. I will say phases do not always have to be present. But if a phase is present anywhere, then a phase should be present everywhere. Do we know what AQ means? Aqueous. And what does aqueous mean? Jacob? Good. Aqueous tells us that this is dissolved in a solution with water. I think aqueous is a very important phase of matter. For instance, you all know sugar. Sugar at room temperature is what phase? It's a solid. We give it that X symbol. Has anybody ever heated sugar up on a pan or in a cup or whatever in boiling water? And you've turned solid into a liquid, right? What does the sugar behave like then? Turns into like a syrup. Liquid sugar is a syrup. Have you ever dissolved sugar in water? Is it a liquid? Would you give that sugar the abbreviation L? Does it behave like a syrup? What happens when you dissolve sugar in water? Just disappears and it makes the water sweet, right? Similarly with salt, NaCl is a solid. You need to get sodium chloride up to hundreds of degrees Celsius in order to melt it into molten salt. And at that point, it's incredibly hot. Don't ever try to do that at home. But you can just take some sodium chloride and dissolve it in water. Aqueous, is that the same as being a liquid? No. So the aqueous state of matter is very important. It is not a liquid state of matter because we know for all of these chemicals that being a liquid gives us different chemical properties. But being aqueous, just being a solute dissolved in water, gives us unique physical properties. So yeah, we're all very familiar with solid, liquid, gas. Aqueous is kind of this weird, ambiguous phase of matter, but it's an important one. Okay, anything else that you guys recognize here? We've got the chemical species, we've got their state of matter, we've got these symbols, and then we've got coefficients. By the way, any math people in here? Tell us what coefficient means. That was actually a very good definition. The coefficient is the number before a variable. I want to say co there probably has something to do with like co-pilot, co-parent, cooperate, coordinate, coefficient. But I'm not really sure what the word coefficient is meant to tell us. Does every chemical have a coefficient? Okay, the twins up here are saying yes and no. One's saying yes, one's saying no. Anybody else? Yes? Kind of a very small yes. Anybody want to argue that they all have a coefficient? There's a 1 before C? How come? Exactly. C would not be there if it was a 0. We wouldn't write it. So it must be a 1, and it must not be any other number, otherwise we'd have to say that as well. So coefficients 1 is always assumed. And now this is not entirely obvious here, but when we look at a chemical reaction, a chemical equation, we want to say that the coefficients are always at their lowest ratio. Could I lower the ratio of the coefficients here at all? Could I divide all of these coefficients by the same number to get a lower set of whole numbers? Well, first of all, the lowest number is 1. So, no, I can't. If I divide everything by 1, nothing changes. If I divided everything by 2, I could get 2 down to 1 and 4 down to 2. And then I'd get 3 down to 3 halves and 1 down to 1 half. Lowest ratio of whole numbers. This is actually what we call a balanced chemical equation. All right, so what I want you guys to do is take questions number 1 and 2 under correct the chemical formulas. I want you to decide what might be wrong with these equations and fix them. Rewrite them or fill in what's necessary to correct these chemical equations. And then we'll move on to our next part of really getting into the balancing. Let's spend no more than 5 minutes on this, yeah? So as soon as you're done, look around to see who you can talk with. In the next part, we'll need that. Great. I have a typo on number 1. It says 6HCl, 3CaOH2, and then it says 3H2O. It should actually be 6H2O. It's not balanced. And the goal was not to have you balance that, because as you can see, we're going to do the balancing next. The goal was just to have you address the lowest ratio. So this is what was wrong on number 1. That should have been a 6, and that will change how you correct it. So what do you guys notice in number 1? Can divide by 3. All of those coefficients can be divisible, are divisible by 3. So what coefficients should I get? Just list the 4 coefficients. 2, 1, 2, 1. Do I need to write out the 1? No. In fact, it'd be better to rewrite this without the 1s. We would say 2HCl reacts with calcium hydroxide to give 2H2O and calcium chloride. What do you guys notice is wrong in the second one? Hold it. Does it have the lowest ratio of coefficients? Okay. Is there anything wrong with like the plus sign? Is there a minus instead of a plus? No. Is the reaction arrow present? Okay. What's missing then? Is a chemical written incorrectly? Is the chemical formula wrong? What's missing? Is there an oxygen missing? Ah, yeah, but actually, so there's 3 oxygens on the reactant side, and there are 3 oxygens on the product side. That's good. We'll talk more about how to look for those balancings. Berkeley? Right. One phase of matter is present, but not all of them have their phase of matter. What is the phase of matter at the start, the reactant? So we've got dissolved carbonic acid. What phase can we predict for the H2O that is produced? Probably a liquid, since this is already surrounded by liquid water. What about the carbon dioxide? Can we predict the phase of matter that the carbon dioxide has? What would you predict? Why a gas? We know carbon dioxide. If you don't know carbon dioxide, it's in your lungs and your bloodstream right now. Get to know it. Carbon dioxide's a gas most of the time, especially at room temperature and pressure. So we have good reason to believe that this would produce a gas. In fact, this is what's responsible for the fizzing when you crack open a soda. All of that CO2 is coming out of the water, bubbling out. Would you guys believe me if I had put a different reaction arrow in here? If I had put this equilibrium or two-way reaction arrow, do you feel like this is possible? Because you guys will believe me no matter what I say. Maybe. I could say something totally wrong. Would you be surprised to see that arrow? Would you be skeptical of it at all? Okay, so you know that water and carbon dioxide surround each other all the time, and that it doesn't seem like this is readily happening, where carbon dioxide and water are reacting to form carbonic acid. Not under normal circumstances. Okay, or maybe it does happen, but it's to a very small extent. And if you have a larger and larger amount of either of those chemicals, then the chance of that small extent happening increases because you now have more and more of them. This does happen. This reaction, two-way reaction arrow, is correct. There is an equilibrium where more often than not, carbonic acid decomposes. But if you push carbon dioxide into water, you can cause it to react with the water and form carbonic acid. Two instances. One, with your carbonated drinks. You've got CO2 that is dissolved, and you also get a small amount of CO2 that is reacted with the water, and so it forms carbonic acid. Increases the acidity a little bit. The other more pressing place is actually in our oceans. More CO2 in the atmosphere means more CO2 possible of running into the water in the ocean. So when you hear about scientists talking about the acidification of the oceans, rising ocean temperatures and rising acidification, this is what's happening. Higher temperature allows this backwards reaction to occur more, and this is the result of making our oceans more acidic. Because once this does form, it can give away a hydrogen through an acid-base reaction, and then it doesn't decompose as readily. So now it has created carbonic acid, distributed that acid into the water, and now it won't go backwards. Okay, now we're going to dive into balancing equations. How many of you have done an exercise of balancing equations before? Okay, anybody, this is your first time balancing a chemical equation? Okay, let's talk about the rules. A balanced chemical equation obeys the conservation of mass law, which means I'm not producing mass, I'm not destroying mass. And within our class, we're not going to be changing elements either. We're not going to be doing nuclear reactions, which means that we're not going to be creating atoms of a certain element. We're not going to be destroying atoms of a certain element. So we want to have an equal number of each element on both sides. On the reactants and on the products. Equal number of carbons, equal number of hydrogens, or an equal number of iron atoms. Sometimes fractions can actually help us shortcut the balancing process. So we're not allowed to place fractions, but we can use fractions on our way. Fractions are not allowed. But are useful in shortcuts. All right, let's go through this first reaction together that's on your sheet. C2H2 plus O2 reacts to form CO2 plus H2O. This is a combustion reaction. I think I've talked about this chemical before, C2H2. Does anybody recognize it or remember what it was? This is acetylene gas, which is a good fuel and really useful in things like welding. I'm going to use a method that I call accounting. So I'm going to divide my chemical reaction into two sides, and I'm going to list all of the elements that I have on either side. I have carbon, hydrogen, and oxygen. And I'm going to list them in the same order on both sides. And to be fair, this order for these atoms is not random. It's always best to try and balance your carbons and hydrogens first, and then balance your oxygen second. The reason is the carbons and hydrogens are simply easier to balance on their own, and the oxygen can be manipulated a little bit differently than either of them. So we have a better way of balancing oxygen after the carbons and hydrogens are balanced themselves. So, as it is, my left-hand side has 2 carbons, subscript 2, 2 hydrogens, and 2 oxygens. Raise of hands. How many carbons on the right-hand side? Ryan. How many hydrogens on the right-hand side? Gerardo? 2. I saw your mouth moving. I just needed the words to come out. How many oxygens on the right-hand side? Daniela? 3. The oxygens here are a little bit trickier. You notice there are oxygens in 2 places, but you've got to actually count the subscripts. 1, 2, 3. All right, let's start by balancing the carbons. We're going to add coefficients in order to change the quantities. Should I add a coefficient to the left-hand side or to the right-hand side of my chemical equation? Add a coefficient to the left-hand side, increase the number of carbons on the reactants. Well, it's true, if I place a coefficient here, it's going to change not just carbon, but also hydrogen. But do I want to increase the number of carbons on the left-hand side? So should I add a coefficient here? No. Where do I want to add a coefficient to balance my carbons? I want to add a coefficient in front of carbon dioxide. Do you guys agree? What coefficient would allow me to balance my carbons? A 2. A coefficient that multiplies with the subscript to give me a number of carbons that balances with the left-hand side. So I'm going to put coefficient 2, and I'm going to rewrite that my number of carbons is also 2. Before I do anything else, I'm going to go through and see if any of my other atoms are now changed in their count. Hydrogens, does this coefficient 2 change the number of hydrogens? No. Oxygens, does this coefficient 2 change the number of oxygens? 2 times 2 gives me 4 oxygen atoms here, plus 1, 5 oxygens on the right-hand side now. Now let's balance hydrogens. Should I add a coefficient to the left-hand side or to the right-hand side to balance my hydrogens? Good job. Actually, I didn't think of it as a trick question, but you're right. Hydrogens are balanced. Sorry, I wasn't expecting that. 2 hydrogens on the left, 2 hydrogens on the right. Great, no coefficients necessary. So now we move on and try to balance our oxygens. This is where fractions can be useful, because notice how I have an odd number of oxygens on the right-hand side. In order to get an even number of oxygens to balance with an odd number of oxygens, a coefficient would be really useful. Or excuse me, a fraction coefficient would be really useful. For instance, what number could I multiply by 2? What number could I multiply by 2 that gives me 5? 5 over 2, or 2.5. I could put 2.5 or 5 over 2. Either one is technically a fraction, so you can write either way. But 5 over 2, 2 now becomes 5. Did I change my number of carbons? Did I change my number of hydrogens? The chemical equation is technically balanced, but I've used a shortcut. I'm not actually allowed to report this set of coefficients. So now how do I move from here into the true balanced equation? Well, I'm not allowed to have that fraction. So I'll multiply by whatever number helps me get rid of that fraction and keep the lowest ratio. Here, Sarah, take a worksheet. So what should I multiply by? Multiply by 2, which cancels the 2. I cannot multiply just one of the chemical species because technically this is balanced. There are an even number, an equal number of every element on either side. So I don't want to change just one chemical species coefficient. I want to change all of them. So I'm going to take this chemical equation and I'm going to multiply the whole, I'm going to multiply the whole chemical equation by 2. 2 times 1? 2. 2 times 5 halves? 2 times 2? 2 times 1? That's my new chemical equation. 2C2H2 reacts with 5O2 to give me 4CO2 and 2H2O. Two, 5, 4, 2. You can double check. Is there a lower ratio at all for that chemical reaction? Is there any number in common between all the coefficients I could divide by? That 5 throws everything off. And if you wanted to check your accounting one more time, On the left-hand side, I now have 2 times 2, 4 carbons. On the right-hand side, I have 4 times 1, 4 carbons. On the left-hand side, 2 times 2, 4 hydrogens. And on the right-hand side, 2 times 2, 4 hydrogens. On the left-hand side, 5 times 2, 10 oxygens. And on the right-hand side, 4 times 2, and 2 times 1, 2, 8 plus 2, 10. Let's do a problem that's not quite as involved, that doesn't need these coefficients. I'm going to let you guys do the rest of that worksheet, but I want to give you one more really common example. This is a chemical process called the Haber-Bosch process. This is how we produce ammonia that is then put into fertilizers for nutrients for plant growth. We take elemental nitrogen, N2, elemental hydrogen, H2, and we make NH3. Let's balance this one again together. On the left-hand side, all I have is N and H, and on the right-hand side, N and H. How many N on the left-hand side? How many N on the right-hand side? H on the left, H on the right. So far, easy enough. If I started balancing with H, it might be a little bit tricky because I can't get either one of these to the other unless I use a fraction, but why don't we start with the N, since it would be really easy to start there. What coefficient can I add to what chemical that balances my N? Raise of hands. Danila? 2 on the right-hand side. A 2 in front of ammonia. That changes my number of nitrogens. 2 times 1 is 2. Does it change my number of hydrogens? 2 times 3, 6. Well, now it's actually really easy to balance my hydrogens. What coefficient can I add to what chemical to balance my hydrogens? Raise of hands. You've done a great job, Danilo. I'm going to wait for somebody else. What chemical coefficient in front of what chemical species to balance the hydrogens? If it feels easy, then just answer it. A 3 in front of H2. This takes 3 times 2. This takes my hydrogens to 6. Does it change my count of nitrogen at all? Okay, then we're done. 1 molecule of N2 reacts with 3 molecules of H2 to give 2 molecules of H2O. By the way, this is scalable, which means the equation can also read 1 mole of N2 reacts with 3 moles of H2 to produce 2 moles of NH2. All right? So we're going to take the next 10 minutes to see how far you guys can get on balancing these other chemical equations. 2, 3, and 4 are all combustion. And then 5, 6, and 7 are other types of chemical reactions. Here's the deal. If you're struggling on one of the combustion reactions on the front page, flip to the back and do 5, 6, and 7, which are easier, in my opinion. And then come back and see if your skills have been refined at all to do the ones on the front. I'm going to be walking around, so please let me know if you have questions so I can help you. Even if you're not sure what your question is, I'll watch and try to give you some help. Feel free to collaborate. This is absolutely a time to work together. question.
I didn't see
If they're not changing,
I was actually getting there. See, I had
then yeah, just count them as one. It'll save you the work. Great,
Oh, yeah.
great observation.
So it'd be 1, 3,
3, 2, 3.
Mm-hmm. Yeah. So far, so good. I don't think you have 9 O's here. Yep. That's true. But yeah. Yep.
What's this 3 right here?
I don't think it's different. But you got it scheduled. Good. You got it right.
It's a 2-hour time, right?
3.
Oh, is it?
Yeah.
Oh, no, I have it scheduled for hours.
Oh, really? I thought it automatically told you. Like when you were.
Well, I don't know. I didn't pay attention to it. I was thinking it was a 2-hour one, so I was like, well, if I turn them in by 5,
Yeah.
then I'll have time to.
I always forget that.
So the unit tests are to
Try his strategy.
and that was intentional as a way of saying if you can do the unit test in 2, then you have more time to get better on the exam. But I think you can do it still in 2 hours. Actually, I think it's less than 50.
Oh, really?
I think it's 40.
Okay, so as long as I'm quick on one,
It might be 50. But yeah. Mm-hmm.
so that's good. That should be okay.
It should be. I agree.
I don't usually take full time.
I'll call it good. I'll call it doc. Good.
Okay.
Bye. Bye. Did you get a sheet? Yeah, it's in my pocket. Okay, good.
Oh.
Right? One cover. 2 hydrogens right here.
Okay, cool.
And then you have our oxygen. Yeah. Yeah. How about that? I'll get picked on. It's just there's 2 of us. Is there a typo in number 5?
Number 5.
Because isn't that just already balanced?
That's what you got to figure out, man. No, I don't think there's a typo there. Yeah, maybe it's strict, maybe it's easy, maybe it's handing you one. Still got to prove it, right? I mean, if you proved it in your head, that's good.
Yeah. I'm writing all these things down.
Does anybody want me to wait to erase this example we did together? Do you want some time with it?
Yeah.
Okay.
Is that it? We got 2 hydrogens. 4 hydrogens. So 4 hydrogens. 1 nitrogen. 2 oxygen. 1
So is there a way that
Oh, wait. Yeah, sounds good. Yeah, you're on the right. Yeah.
What would I get?
I think it's gonna be 1, 3.
So yeah, okay, 6. Yeah.
So how I have it right now?
So you would multiply just 8 by 2.
Yeah.
I don't think
So
so.
now 6 plus 1 is 7.
Well, so let's do that.
That was actually surprisingly easier.
12 on this side. 2
Good, good.
phosphorus on this side, 2 on this side.
This one is crazy, so we're gonna do
Yep.
Okay.
It is. Isn't that crazy?
Yep.
That's octane, by the way. That's your car gasoline. So think about that. Every molecule of octane that you're burning, you're taking 20, or I guess for every 2 molecules of octane, you're burning 25 molecules of O2. Instead of breathing in that O2, right? And then look at how many molecules of CO2 you're taking out. Every 1 molecule of octane makes 8 molecules of CO2. Love it. Mm-hmm. To be fair though, your sugar that you eat and metabolize, you make 6 molecules of CO2 for every molecule of fructose that you take in. But you're burning that at least. You're alive. You're not just a car propelling down the highway. You guys feel good? Sweet. This one's pretty easy, right? Back side. Okay, if you haven't already, if you're still on the first 4, I want you to spend a few minutes on the back side. Has anybody not gone to the back side? Okay, flip to the back side then, and spend a few more minutes before we wrap this up, solving on the back side. Because the front side is the hardest, but the back side is much easier. So spend a few minutes on there. Good. No work though. Is your work all in your head?
Yeah, I do it off the dome.
You too?
I did on this one.
Good. That was the easiest one. Here's the deal about doing
this
work.
one was easier.
You think so?
I think so.
I took all of that space to do it.
I did. We did it in our head pretty quick.
Wow. Okay, well, you guys have some background in chem.
Yeah.
This is not your first time balancing equations.
Yeah.
So it's been a few years.
It's been a while.
Okay.
How to go to the chemistry teacher that I used to be.
Yeah. Okay, good. But just remember, developing that skill means that when you get stuck, you know how to lean into the skill.
I could do it if it came out.
Good. As long as it makes sense, I can't force you to do it. Actually, we, as chemistry instructors, have been talking about forcing you guys to show your homework for 1 problem on every unit. Because we've noticed, one of your classmates actually brought this up. Like, how do I show the work I did on the exam? You don't show the work you did on the exam.
Yeah.
But if you're not being forced to show your work, then you might not be doing your work, and it's doing the work that teaches you the skill better. So I feel like we're failing students there. We're not actually forcing them to do the work. Except for in a moment like this, where I'm kind of forcing you to. But I'm not even forcing you. I wouldn't give you a grade.
Yeah.
So we're thinking about like every unit, you have to upload 1 problem, 1 solved problem. And then for every exam, every like unit test, you have to show your notebook to show how you've been staying caught up in the class. As a way of like checking that you're actually
That you
engaging.
actually know what you're doing.
And honestly, it'd probably be better for online students because my online students don't get this chance where I can force them to sit down and do their work.
Yeah, I mean, that's basically what goes on in my head right there.
Good.
Pretty much the same thing, so.
Are you a pretty visual guy in your head?
Yeah.
Like, do you see that?
Uh-huh. Yeah.
Good. Certainly helps.
I'm just trying to see if it's like this. I'm just trying to do it like this though. Just for the sake of the PhD.
Great. here's I'll show you what. Multiply by 2 divided by carbon. Multiply by 3 divided by hydrogen. You get 7 oxygens here. And you get 3 goes to the Yep. So 2 times 2 is 4, and 3 times 1 is 3, so it's 7. No. Here you start out with 3, 1 plus 2. So how do I get 3 to 7? I can't really. But where do I start? Do I add a coefficient here, or do I add a coefficient here? So if you guess and check, what if I added 2? And that's 1 plus 4. It's 5. Okay, 5 is that's close to 7. So if I add 3 times 6 plus 1 is 7. It's actually just a coefficient of 3.
I think I just missed that off.
Okay. Yes. Actually, that would do it. Otherwise, you would have been right on track. Yeah. And let me see your problem. I think it's probably the same deal here. So I think you want to.
I keep missing my off.
Yeah.
Thank you.
You got it. Tell that how you got it. Mm. So in this problem, you got to a point where you had 2 O's here and 25 O's here. And then you used 12 over 2 times 2 gives me 12. So what I actually want, I want 25 O's. So I want 25 over 2 times 2. And then multiply everything by 2, and then actually everything else works out. So that 12 becomes a 25, and you're good. Okay. You want a new sheet? Yeah, you got it. All right. Why don't we, do you want to solve it and then take a break? Or do you want to take a break and then solve it? All right. So let's go through these together. The first reaction I showed you in balancing the equations was balancing combustion of acetylene. That was the one we went through together. And then the one after that is the combustion of octane. So this is the gasoline in your car. When you're driving down the highway, this is the chemical reaction that is allowing you to move forward. We start by balancing all of our atoms. And we take the easy route. We start by balancing our carbons. I'll just place a coefficient 8 in front of carbon dioxide. That means 8 times 2 is 16 plus 1. Now I have 17 O's on the right-hand side. Hydrogens don't change. I'll balance my hydrogens. I'll place a 9 coefficient in front of H2O. That gives me 18 hydrogens on the right-hand side. 9 times 1 is 9, plus 16. Don't feel bad if you need a calculator for that. I'm just going off what you guys showed me earlier, actually. But 9 plus 16 is 25. Okay, checks out. So I have 2 oxygens on the left, 25 oxygens on the right. There's only one place where I have oxygens in this chemical reaction on the left-hand side, and that's O2. So I need to multiply 2 times some number such that I get 25. What number can I multiply by 2 to give me 25? 25 over 2. Okay, we're done. Submit it. No, lose points, right? To get rid of that fraction, I need to multiply every coefficient by 2. 1 times 2 2. 25 times 2, 25. 8 times 2, 16. 9 times 2, 18. So here's a cool way to think about this. For every 2 molecules of octane that you burn in your car, you're pumping out 16 molecules of CO2. For every 2 molecules of octane that you burn, you need 25 molecules of O2. Think about that on a larger scale. When you burn 2 moles of octane, and we could figure out how much 2 moles weighs. When you burn 2 moles of octane, you're using 25 moles of oxygen, and you're pumping out 16 moles of CO2. Now, here's something I know some of you missed. In 3 and 4, oxygen is present in more than just one place. So when I start balancing these, I get 2, 6, and 3 oxygens, 1 plus 2. This is number 3. So what? I've got 2 oxygens plus 1. So I've got a total of 3 oxygens on the reactants, 1 carbon on the products, 2 hydrogens on the products, and 3 oxygens. Whew. Oxygens are balanced, finally. Makes it easy, right? Wrong. Start by balancing the carbons. Coefficient 2 in front of carbon dioxide. Now I've got 2 times 2 plus 1. I've got 5 oxygens on the product side. Balance my hydrogens. I need a coefficient 3. Now I've got 6 hydrogens, but 2 times 2 plus 3 times 1, 4 and 3 is 7 oxygens on the right-hand side. So now that carbon and hydrogen are balanced, oxygen is unbalanced. I need to rebalance my oxygen. But there's 2 sources of O. There is no easy way to get 3 up to 7, correct? Because they're both odd numbers, I'd have to find a number they have in common. And if I did find a number in common and then just work to get them both there, I'd still have to decide what coefficients do I place in front of each source of oxygen. So let's just do a guess and check. If I added any coefficients in front of this compound, this is ethanol, by the way. Ethanol is another chemical inside of your gasoline that helps remove the knocking in the engine. Ethanol, changing any coefficient in front of ethanol is going to change my count for carbon and hydrogen. So I want to avoid placing a coefficient there at all costs possible, by all means possible. So I'll start by guessing about coefficients in front of O2. What coefficient could I place in front of O2 that might get my total up to O, recognizing that I'll get 1 additional oxygen from ethanol every time? So if I placed a 2 in front of O2, I'd get 2 times 2 plus 1, 5, which is actually closer. If I place that coefficient 3, 3 times 2 plus 1 is 7. I didn't even need to use any fractions for this one. But I did have to guess and check about how should I place coefficients. So 1 molecule of ethanol with 3 molecules of O2 to make 2 molecules of CO2 and 3 molecules of water. Any questions on those ones? By the way, if you need a new sheet, you can always come up and grab one, or I can hand one out. I know some of you really used up that space to do your work, which is what it's meant for. All right, let's solve the last one. I'm going to have to get rid of one of these examples. Does anybody know this chemical? C3H8O. This is the combustion of isopropyl alcohol. And isopropyl alcohol is kind of common as like a little fire. Some of you may have these like indoor fire pits where you pour isopropanol in it and then you light it on fire and it just burns above it. So I'll start with carbon, coefficient 3. Again, I've got 3 times 2 plus 1. Balance my hydrogen. I'll put a coefficient 4 in front of H2O. And now I've got 3 times 2 plus 4 times 1, so 6 plus 4, 10 oxygens. And now I've got the problem, how do I get 3 balanced to 10? If I put a coefficient in front of isopropanol, I'm going to have that same issue of running into imbalance between carbon and hydrogens again. So can I get a number in front of O2 that balances my oxygens alone, even if this time it needs to be a fraction? Let's say it this way. What number of oxygens plus 1 would give me 10? 9 oxygens plus 1 oxygen gives me 10 oxygens. So how do I get a 9 in front of O2? How do I get 9 oxygens out of O2? We don't need to times everything by 2 yet, but we actually had the same problem when we were up above. We said, how do I get 25 oxygens out of O2? I needed to multiply by 25 over 2. How do I get, I kind of forgot what we even did with acetylene. So if I want to get 9 oxygens here plus 1, I need to have 9 over 2. That coefficient times the subscript 2 gives me 9 oxygens. 9 halves times 2. By the way, what is 9 halves as a decimal? I could have also put it that way. What number times 2 gives me 9? 4.5 times 2 gives me 9. Plus 1. Now I've got 10 oxygens on the left-hand side. But this time I can't just submit. What do I need to do? I need to get rid of the fraction, multiply everything by 2. So instead of 1 CH3OH, instead of a 1 here, I'd multiply by 2. 9 halves times 2, 9. 3 times 2, 6. 4 times 2, 8. We can go through and check again. Now I've got 6 carbons. I've got 16 hydrogens. And this gives me 18 plus 2, 20 oxygens. 6 carbons, 16 hydrogens. 6 times 2 plus 8, 12 plus 8, 20 oxygens. So we've just gone through to prove that we did it right. Okay, those were the hardest ones by far. On the backhand side, we had copper plus sulfuric acid forms hydrogen gas, elemental hydrogen, plus copper sulfate. What coefficients did you add to this chemical equation? None. That chemical equation is balanced 1 to 1 to 1 to 1. What about number 6? Nitric acid plus magnesium hydroxide forms water and magnesium nitrate. What coefficients did you put? Put them as a list of 4 numbers. Not nothing, but 1. You leave it as 1. 2, 1, 2, 1. 2 moles of nitric acid reacts with 1 mole of magnesium hydroxide. to give 2 moles of water and 1 mole of magnesium nitrate. And the last reaction, phosphoric acid plus sodium hydroxide react to form water and sodium phosphate. 1,3,3,1. 1 mole of phosphoric acid with 3 moles of sodium hydroxide to give 3 moles of water and 1 mole of sodium phosphate. Backside compared to the front side, much easier. Combustion reactions in general are the hardest ones to solve, but precipitation reactions, acid-base reactions, much easier. A tip about solving it on the backhand side. You actually don't need to go through as much work to solve some of these polyatomic ions. I know some of you probably wrote out sulfate as S, O, and as all of the S's and all of the O's separately. But since I have sulfate and sulfate, I can just balance how many of my sulfate ions I have. The same thing with nitrate and nitrate. I can just balance how many nitrates I have rather than balancing oxygens. This is especially nice because oxygen shows up in more than one place. So counting it all and balancing it all gets really tricky. But nitrate is always the same. In fact, we're going to learn about this in our acid-base unit, but water can be thought of as a hydroxide unit. So here's hydroxide, plus an H. So you could have gone through and balanced this as H, nitrate, magnesium, and hydroxide. Separating on the product side, the fact that your water is actually one H and one OH rather than 2 H's and 1 O. You can look at those chemical species as combinations of ions rather than needing to count every element on its own. You're still balancing appropriately. All right, let's take a break, about 5 minutes, and we'll come in to wrap up our lecture by diving into another type of chemical reaction. All right, guys. The next part of balancing reactions, it actually introduces two specific types of chemical reactions. We're going to look at ionic reactions. And we're going to see that ionic reactions have different ways that they can be written, different names, describing what's included in those different forms. The first is the molecular reaction. The distinction here is that we're simply writing out the chemical formula of the ion. We should still include phases when necessary. And of course, to be balanced, we're still looking for the lowest ratio of whole numbers. On your worksheet, I've given you a molecular equation. I did forget to put in the phases. So here are the phases that we would be looking at. This is lead to nitrate, aqueous, reacting with iron 3 chloride, aqueous. And I would like for you guys to add aqueous next to lead nitrate and iron 3 chloride because without them, doing this ionic reaction is a little bit more challenging. And we see the products here are lead chloride, solid, plus iron nitrate, iron 2 nitrate, aqueous. The fact that lead chloride there is solid is significant. It actually gives us a lot of information going into the next part. What you'll see about the molecular reaction, or the molecular equation, is that entire ionic formulas are just written together and then they're given their phases of matter. The next type of format is our complete, oh, I erased that, but I didn't mean to. The complete ionic equation. It takes those aqueous compounds, those compounds that are not actually experiencing ionic forces, but have been pulled apart by solvent molecules and are now behaving as ions dispersed in solution. It takes those aqueous compounds and it writes them out as their separate ions. So lead nitrate becomes lead ion. What is the charge on this lead? +2. Oops, that feels weird to write it that way. And we're going to keep the phase, aqueous. Plus, there is nitrate. What's the charge on nitrate? This is one you need to know. This is what? NO3 -1. NO3 minus. This is actually how we can figure out the charge on lead. Lead 2 plus, because I've got 2 NO3 minuses. Now, when I separate lead nitrate into its ions, I need to recognize that there are 2 ions of nitrate. That subscript 2 becomes a coefficient 2 in the complete ionic equation. Does that make sense? If it were a chemical, lead nitrate would bring 2 equivalences of nitrate. But since it's not even a chemical, they're dissolved in water, they're separated as ions, there are 2 ions of nitrate, no more subscript. That subscript becomes a coefficient. And the phase, aqueous. Can you tell me how I would separate out FeCl3 aqueous? Raise of hands.
It'd be Fe3 plus aqueous plus CL3 or CL3
Cl3 minus aqueous? No. Anybody want to point out the mistake here? Jacob? We know Cl minus is 1 ion, and there are 3 of them in FeCl3. So that subscript 3 needs to become a coefficient 3 in the complete ionic equation. It's not Fe3 plus and Cl3 1 minus, yeah? It's Fe3 plus and 3 Cl minus ions. Good. All right, now on the other side of my equation. Does lead chloride, PbCl2 solid, separate into ions? No, it's not aqueous. That does behave as a molecule. I can't take a solid and say this behaves as 2 ions dissolved in solution because it's not dissolved in solution. So this becomes, I should say this stays PbCl2 solid. Solids do not separate in our complete ionic equations. Tell me what else I get. Should Fe iron 3 plus nitrate stay as iron 3 plus nitrate? Tell me one thing I get. Fe. Oh, I did mess up, didn't I? Or did I just copy it down wrong? Just tell me I copied it down wrong. I just copied it down wrong. This is FeNO3 3. So the charge on iron, 3 plus, aqueous. And the charge on nitrate, minus, aqueous. And that coefficient 3 becomes, or excuse me, that subscript 3 becomes a coefficient 3. What's one thing we haven't done yet? I skipped over it. Did we check that this equation was balanced? Is it balanced?
Looks good to me. It looks off. Looks a little off to me.
It is off. So we probably should have balanced first. But we can balance both of these at the same time. We can show how some of that work goes into it. So one lead on the left, one lead on the right. Great. One iron on the left, one iron on the right. Great. 2 nitrates on the left, 3 nitrates on the right. How am I going to get those to balance? Just add 1 here, which would actually be adding 1 nitrate out of a compound that adds 2, which is 3 over 2. I'd be adding 1.5, which I can't do. So, Daniela? Thank you, guys. One more time? Good. This works very much like the crisscross method in balancing a chemical equation, or an ionic formula, right? If I know that I've got 2 here and 3 there, I can only get to 6 of each. So I'll get 6 nitrates, coefficient 3, and 6 nitrates, coefficient 2. Now my nitrates are balanced at 6 on both sides. Are you guys okay with that? We could still use our shortcut method of the fraction. We would have done 3 halves to get 3 nitrates here, and then we would have left this as 1 to get 3 nitrates here. And we would have had to multiply by 2 at some point anyways. And 3 halves times 2 is 3, and 1 times 2 is 2. What about my chlorides? Are my chlorides balanced? 3 chlorines on the left, 2 chlorines on the right. What can I do? Same crisscross method. I'm going to have to get to 6 chlorides each. So a coefficient 2 in front of iron 3 chloride, a coefficient 3 in front of lead chloride. I want to go back and make sure my lead and iron stayed balanced. 3 lead, 3 lead. 2 iron, 2 iron. All right, let's talk about how if we had this balanced coefficient, this balanced chemical equation, and then we tried to do the complete ionic from there, what would we have gotten? Well, again, this separated into 2 nitrate ions, and I've got 3 sets of this chemical. Or I can just take this coefficient, and I now multiply it down below. 3 times 1 is 3. 3 times 2 is 6. I've got 2 nitrates and 3 lead nitrates, so I've got a total of 6 nitrate ions. What coefficient do I give iron? A 2. What coefficient do I give chloride? A 6. Because I've got 2 iron 3 chlorides, each containing 3 chlorides. 6 for my chloride. What coefficient do I give iron or lead chloride on the right? Yeah, that coefficient stays the same. Nothing changed there. Just to double check, 6 chlorides on the left, 3 times 2, 6 chlorides on the right. Coefficient in front of iron? Yeah, it should balance what I had before and up above. Coefficient 2. Coefficient for nitrate? 3 times 2, 6. Great. This is what we call a complete ionic equation. Every ion that's present is written out. And if ions are not present, but instead ionic compounds are present, they're written as an ionic compound. The last type of format that we have is the net ionic equation. I'm going to take you guys through the net ionic equation for this one and leave the other one for you guys to solve. Number 5, that is, on the back. 9. When we write a net ionic equation, we're removing what we call spectator ions. I know some of you guys are athletes. Do spectators ever get involved in the game? They shouldn't. And what about some of these ions? Are any of these ions really not doing any of the chemistry? Can you point out an ion that is not changing during this chemical reaction? NO3 is not changing. It started as an ion. It ended as an ion. What else? Yeah, iron 3 plus and iron 3 plus. They are spectating a chemical reaction. The reaction that they are spectating is that lead 2 plus and chloride minus are coming together to fall out of solution. They're going from ions dissolved to ions precipitated, an ionic compound precipitated. These are my spectators. Spectators watch the reaction. They do not change. And just like your net income is whatever your complete income is minus all of your taxes, the net ionic equation is minus the spectator ions. Does anybody want to tell me what the left-hand side of my chemical reaction reads for the net ionic equation of this reaction? What's the reactant side? Cole? Chloride, aqueous, yep. Yes and no. Or what I would say is a good start. Our coefficients are not there. Let's copy the coefficients exactly as they appeared in our equation. And then let's see if those coefficients are really the best. So 3 lead 2 plus and 6 chloride minus gave me 3 lead chloride. Is that the correct balanced chemical equation? You want to tell us why? Good. All of those numbers are divisible by 3. It is true that from the molecular and the complete ionic, those were the coefficients we needed to have a balanced chemical equation. But considering the fact that iron is not actually involved in the reaction, and nitrate is not actually involved in the reaction, this is not the appropriate chemical formula or the appropriate chemical equation. The appropriate chemical equation is 1 ion of lead plus 2 ions of chloride make 1 equivalence of lead chloride. Did I say iron again? I'm sorry. I think I might have mixed up my ions. 1 to 2 to 1. Divide everything by 3. That's my balanced chemical equation. And I will say on unit tests and on the exam, you'll have questions that say which of the following is the balanced net ionic equation, and both of those will be an option. So let's reaffirm. Why can we say with confidence that this is the correct net ionic equation from this ionic reaction and not this? Why is this the correct balanced equation? It's the lowest ratio of whole numbers in the coefficients. That's the definition. This isn't necessarily false, but this follows the definition. So what I want you guys to do is that second one starts as a complete ionic equation. I want you guys to balance it and then determine the net ionic equation. You could also even take a second to try and work backwards and figure out the molecular equation that came from it. That is our time for today. So if you want me to check your work before you head out, I'm happy to do that. Otherwise, we're going to pick up on Wednesday with this bottom part, and I think I'm going to bring in another worksheet for us tomorrow, Wednesday. We're going to dive into 3 types of reactions together. Okay, have a good night, guys.